Hello, I'm Dr. James Dborin, co-founder of Doubleword AI, and today we're back with another Behind the Stack YouTube video where we're going to be talking about speculative decoding. Speculative decoding is an inference optimization technique that has got a lot of attention over the last couple of years since it was released for its ability to accelerate the inference of large language models. And today we're going to talk about speculative decoding. We're going to discuss what it is, how it speeds up language models, and then considerations for where do you find the draft tokens. And the phrase draft tokens is something that you'll become familiar with at the end of this video. So let's tackle the first question with what is speculative decoding. So to do this, we're going to have to look at the dynamics of large language model inference. So if I have a model here, language models inference are split into two phases. In the first phase, you put in your prompt. So this is the prompt that you send to ChatGPT or something. Which is like a long sentence, and this gets processed in one step by the language model. It might be multiple steps, but that's sort of out of the scope for this video. And then the model, as output, produces a single token. Then what you do is the model has now created what's called a KV cache, which is its quote-unquote memory of this prompt. And then what you do is you pass in the previous token that you generated, and then it generates the next token. And then this word gets added into the KV cache. And in the next step, you pass in the next token that you generated. And then you do the same. And so on and so forth. That's why these models are called auto-regressive. They take the output from the previous step, and that becomes the new input into the model. And what you'll notice here is that during the decoding phase, this is the decoding phase when the model's actually responding to you, we lose a lot of the parallelism that we benefit from in the first phase. So in this first phase, what's nice is that maybe we put in like thousands and thousands of words into this model, but they're all processed at the same time in parallel to produce a single token. That's really efficient. It means that we amortize some of the fixed costs associated to language model inference. For example, one such cost that you have to do is in a GPU, you have the weights stored in VRAM, and then you have the sort of compute part of the GPU, the SMs, and you have to move these weights into the SMs before you can do any operations on them. So the nice thing about the prefill stage is we can sort of amortize this over many thousands of tokens. We only do this once for this entire process. And that's really nice. But in the decoding phase, we lose that. So now for every single token, we have to bring in the weights again to the SMs. And this is actually what bottlenecks generation. If you've ever noticed, on like API prices, they often quote like an input and output tokens, and the input tokens will be many times cheaper in many cases than the output tokens. And this is fundamentally why. The input tokens are cheaper to process because they're done in parallel, and you're amortizing some of the fixed costs associated with producing a single token. So in speculative decoding, what we're going to try and do is introduce like a level of parallelism into the decoding stage to try and speed it up and make better use of the resources that you're paying for each token. The name speculative decoding comes from, it was inspired by the idea of speculative execution in CPUs, and I'm no expert on this, but the idea in speculative execution is that the CPU will sometimes execute instructions that have not been explicitly set in your code. Maybe it's like a for loop, and if you're looping over 1 million items, it will execute the same instruction on the millionth and one iteration, only to discover that it can't do it because it exceeded the thing, and then because it exceeded your for loop, and then it goes back and erases what it does. Probably does a lot of clever things along the way, but the goal being that it can skip a whole bunch of the checking if the condition's complete, and just do more operations in order to make it more efficient to do like that first million operation. If you have to clean up at the end, like maybe that's more efficient than checking your if statement on every single step. And this is and speculative decoding is quite similar in principle. What we do is we pass in guess tokens to the model, multiple guess tokens, and have the model, rather than generate the new token, tell us whether the guess was correct. So here's an example. So we have your model, and we've pre-filled, so we have like the KV cache that the model is reading from. And we have the token generated from the prompt. And I produced the word this. So this is going to go into the model. And the model was going to say something like, this is your answer. This was like the model's guess. So if we have let's say we had like the perfect, we knew what the model was going to respond. We put this in before, we put this prompt in before, we're doing temperature 0 decoding, so we know what the answer is going to be. And so we put in like the guess. This is, well, what would happen is we would get, the model's output would look something like this. It would agree with your token. It would always predict the next token that you put in, and then finally in its output it would give you the answer that you were looking for, which was something, some answer. So because we knew what the response was going to be, we can get the answer in a single invocation of the language model rather than 4 invocations of the language model. These 4 tokens are processed in parallel, not in serial. And so in a single forward pass, we get the answer, even though the answer required 4 tokens. And so in principle, this scheme could be up to 4 times faster than normal language model inference. You might think, well, I have these 4 tokens, surely I'm doing 4 times as much work. Like, even though it's in parallel, sure I'm doing 4 times as much work. Yes, you are, but during decoding, you are bandwidth bound. So I was talking about the overhead of bringing the model weights into the sort of GPU compute units. And unlike a modern GPU, if you're processing like less than, let's say, 300 tokens, it's almost guaranteed that you are dominated by that time. And so almost the entire decoding time is spent just pulling the weights into the compute units, and you're only doing that once in this case. So even though you're doing 4 times as much work, you're still going to get potentially up to 4 times faster inference in this case. So this feels great. You've got 4 times faster inference, but the trick is that first you had to have known what the answer was. And that's the difficulty here, is how do you know what the model is going to answer before you inferenced it? We said in this case we'd previously inferenced this large language model, and so we knew the answer. And in that case we've already paid the cost of generating it serially 4 times. We've brought the weights into the compute units 4 times. We've paid that full cost, and then we just do it again and we get a slightly faster answer. So this makes sense maybe as like a caching mechanism. In this way, like my user's answer was stored and then cached for faster responses in the future. But it's not particularly helpful. We haven't actually really saved any compute over the first answer. We'd like even answers we haven't seen before to be faster. So how do we do that? Well, this is sort of fundamentally the big problem in all of speculative decoding research is how do I get better draft tokens? That's what we call these tokens are called your draft tokens. That's your guess at what the model is going to respond, and is how and improving these draft tokens is the key to accelerating language models for speculative decoding. So there's one popular source of draft tokens is to use a smaller model. This is what happened in the original speculative decoding paper. So I have a small model, and then I have a big model. And the small model produces tokens auto-regressively and does so very quickly. It's a very small model, so it can produce sort of a dozen or so tokens much faster than a single language model can. And then I pass these speculative tokens into the model that come from the small token. And the model, in parallel, tells me which ones it wants. So it agrees with maybe the first 4 tokens, and then then it can tell you that it disagrees with these tokens, and then you ignore the rest after the first disagreement. And so now you have these 4 tokens, and then in the next invocation, you pass in this token into the model. And so you've now got 4 tokens for the price of 1. If the small language model is very bad, and it didn't produce any tokens, all of these tokens were rejected, it's actually fine because you still always get the first model for free. So if it disagreed with all of these, you always get at least 1 token out of this process. The model will always tell you the next token. So if you're very strongly bandwidth bound, you're not running at a high batch size, this potentially doesn't have any overhead at all. Even if you're never produce the right token, you're dominated by pulling the weights in, and you're getting 1 token out in the worst case scenario. So in the worst case scenario, it's the same as normal decoding. It doesn't incur any overhead. So what are the upsides or what are the things you need to consider with using a smaller model? Well, the things you need to consider is that the model is small. And because it's small, it's probably a lot less smart than the big model. And if it's a lot less smart than the big model, then it probably produces a lot of tokens that the big model rejects. If you ask it a hard maths question that only the big model can answer, you're going to get a lot of rejections from the big model. And if you're getting a lot of rejections, like maybe you're not benefiting so much from this scheme. I said there's not much overhead in this inference, but you can't start inferencing the big model till the small model has inference. So this does have like a latency penalty. It's not completely free. So small models are not smart and can generate a lot of bad tokens. Another thing to consider is that the small model takes memory. So the small model has its own KV cache. It maybe has its own GPUs. And these are GPUs and memory and KV cache taken away from the big model. So if you're not generating a lot of accepted tokens, you're hurting your big model's performance, where it could have been using the bandwidth and the flops and the VRAM from these additional GPUs that the small model is using. Not to mention the small model is having to run before the big model and incurring some sort of like latency overhead. So if your small model is not producing a lot of accepted tokens, you really would rather not be paying this price. And finally, for many models, there is no associated small model. The one key fact is that the small model and the big model have to share a tokenizer. So what you can't do is use like the Llama 1B to speculatively decode for like the Qwen 235B model, because they don't share a tokenizer. If the Qwen has like a 1B tokenizer, then you can't do this. If the Qwen model has the exact same tokenizer and they need to be exactly the same, then you can do this. A lot of models that you might want to accelerate maybe don't have like a smaller equivalent model with the same tokenizer that you can use. Sometimes you're just stuck and you can't get anything from them. So there's a few other sources of draft tokens that people have looked at. Some ideas include training, an additional head for the language model, which outputs tokens in the future that you can use to speculatively decode from. So each step you get 4 or 5 additional tokens in the future, and then those become 4 or 5 speculative decoding tokens that you can check and get some speed up from. The pro of this is that you automatically share a tokenizer. The downside of this is you need to sort of train these additional heads. It doesn't just work out the box. There are some techniques that use past outputs of the model or like suggested text that the user can pass in. So past outputs or suggestions. OpenAI has this as part of the API. You can pass in a set of texts and speculatively decode off these texts. The pro of this is that, again, you bypass this tokenizer issue. The downside of this is that now it's sort of up to you to provide good text. You're not guaranteed that these texts are good. Good sources of draft tokens. Here at Doubleword, we actually created our own version of this, where we store the past outputs of a model in a big prefix-tree, and as the model's generating, we walk down the tree and find previous outputs of the model. We walk down one of these trees and find previous outputs of the model that share a prefix that the model might continue. So if the model is here, we pass in these continuations and then have the model speculatively code off it, so that commonly requested queries or common phrases from the model end up being accelerated, and that tracks user distribution. As the distribution of outputs change, your prefix tree changes. It's a weighted prefix tree, so it sends you the most common completion. So over time, your model becomes faster and faster and better adapted to your users' tokens. So today we talked about speculative decoding as a method of inducing parallelism during the decoding step and accelerating language model inference. We also talked about where you get draft tokens and the limitations of using smaller models, and briefly touched on some other techniques that people have used to get these draft tokens. Thank you for listening, and we hope you join us in future videos.